Hello everyone, I welcome you all in my channel Learn Math Easily. In today's video, I am going to explain you how to find out number of generators for infinite cyclic group. In the previous video, I had already explained you how to find out number of generators for finite cyclic group. But the procedure of finding number of generators for finite and for infinite is quite different from each other. And generators also differs for finite and infinite cyclic groups. So two proofs will be totally different from each other. Before starting with this theorem, I will explain you what is the concept of this particular theorem with the help of one example. See, consider the set Z of integers. What is this? This is 0 will be here, 1, 2, 3, 4 and so on, so on and so on. And on the negative side, minus 1, minus 2, minus 3 and so on. It is approaching to infinity from right hand side and minus infinity to left hand side. Now this is an infinite cyclic group and it is generated by an element 1. How? Because here 1 into 1 is 1. Every element of Z is expressible as integral multiple of 1. Now 2 into 1 is 2, 3 into 1 is 3, 4 into 1 is 4 and so on. In the same way, minus 1 into 1 is minus 1, minus 2 into 1 is minus 2, minus 3 into 1 is minus 3, minus 4 into 1 is minus 4 and so on. So in this way we are getting both the sides. So 1 is the generator of Z. Now is 1 the only generator of Z, or we can have more than one generators of Z? If you look into this these two particular expressions, we find that take this expression here and take this expression here. We get that 1 into minus 1. Take minus sign here. We get minus 1. 2 into minus 1 is equal to minus 2. 3 into minus 1 which is equal to minus 3. 4 into minus 1 which is equal to minus 4 and so on. Now minus 1 into minus 1, here we are getting 1. Minus 2 into minus 1 we are getting here 2. Minus 3 into minus 1 we are getting here 3. Minus 4 into minus 1 we are getting here 4 and likewise. Here you can see that minus 1 is also a generator of Z. So Z can be expressible as a cyclic group generated by minus 1 also. Along with that, one more thing is there. See, what is the relation between 1 and minus 1? Minus 1, see, this is an additive group. And here minus 1 is the additive inverse of 1. So the conclusion we got from this group is that if we know the generator of an infinite cyclic group, then it will have one more generator that will be the inverse of that generator. If it is a multiplicative group, then the inverse will be a multiplicative inverse of generator. Or if it is an additive group, then it will be an additive inverse of that generator. So this is the main concept of this theorem, and in this theorem we are going to prove three things. That if you know the generator, then A inverse will be if you know the generator A of a group G, then A inverse will also be a generator of G. And these two will be only generators of that group G. An infinite cyclic group will have only two generators, A and A inverse. Other than that, it will not have any other generator. So let's start with the statement of the theorem. The number of generators of an infinite cyclic group is 2. So let's start with the proof. Let G is equal to a cyclic group generated by A, and this is an infinite cyclic group where A is the generator of G. Therefore, for any x belongs to G, we have x is equal to a to the power k for some k belongs to z. Keep it in mind, we always take, while proving the earlier theorems, k belongs to z plus, because order of a divides that fixed number and division is possible when a number is non-negative or positive number. Therefore, for our convenience only, we used to take it as k belongs to z plus. Otherwise, every power will belongs to the entire set of integers, means z, the whole set of integers. Therefore, x is equal to a to the power k for some k belongs to z. Now, x is equal to a inverse to the power minus k, where minus k also belongs to z. Since k belongs to z, therefore minus k will also belongs to z. Now, x is any arbitrary element of G. Therefore, every element of G is expressible as a power of A inverse, which implies A inverse is also a generator of G. We will prove that these two are distinct generators of G, means A is not equal to A inverse. Also, A is not equal to A inverse, because if A is equal to A inverse implies A square is equal to E, which implies order of A is equal to order of G is equal to 2, a contradiction, because G is an infinite group, because G is an infinite group. Now, which implies A and A inverse are two distinct generators of G. Now we will prove that these are the only two generators of G. It can never have a more than two generators. Now, let if possible, let B be any generator of G. As B belongs to G and A is the generator, which implies B is expressible as a power of A, means B is equal to AN for some n belongs to Z. Again, as A belongs to G and B is a generator, therefore A is equal to B to the power n for some m belongs to Z. Now, B is equal to A to the power n and A is equal to B to the power m. So, substitute here the value of B. This is A to the power n whole to the power m, which implies A to the power mn minus 1 is equal to E. But order of A will be the least positive integer such that A to the power order of A is equal to E. Therefore, order of A will be less than mn minus 1. But order of A is infinite. Therefore, such kind of term will not exist. Therefore, mn minus 1 must be equal to 0, which implies n is equal to plus minus 1 by m. N is equal to plus minus 1 by m. Sorry, n is equal to 1 by m. Now, if I will substitute any value for m apart from 1, like if I substitute m is equal to 2, I'll get n is equal to 1 by 2. If I substitute m is equal to 3, I'll get n is equal to 1 by 3. So for any integer greater than or equal to 2, for any m greater than equal to 2, we will get n as a fractional number, not as an integer. Therefore, m must be equal to either plus or minus 1. Therefore, n will be equal to plus 1 or minus 1. Therefore, either b is equal to a or b is equal to a inverse. Thus, a and a inverse are precisely the only two distinct generators of infinite cyclic group G. These are the only two distinct generators of infinite cyclic group G. So that was the last theorem based on the topic of cyclic group. I have done almost everything which was important from the examination point of view and explanation point of view. From next video onwards, we are going to discuss some other topics which are based on the topic of group theory. This topic itself is very useful. We may use this several times in different other topics also. If you like this video, then don't forget to hit the like button. And in future, if you want to see such kind of higher mathematics based videos, then don't forget to subscribe for my channel. Thank you so much for watching this.